Welcome, everybody, to the Physics at York's winter webinar series. This is the first of our monthly events, which will hopefully introduce you to some of the physics research going on here at York. First of all, my name is Dr. Chris Murphy. I'm one of the senior admissions tutors in the Department of Physics here at the University of York, and a plasma physicist, conducting my own research into particle accelerators using lasers. So before we get started formally, there's a few technical notes before we introduce the chair and the speaker. If you're watching live, you can ask questions using the Q&A button on your screen. That'll be available throughout the event, so you can ask questions at any time, but we'll probably wait until the end to pick them up at a sort of Q&A session with our speaker. Should you have any technical issues during this event, like a loss of Wi-Fi or something like that, you can always rejoin the event using the original link. Please remember today's event is being recorded, so you can watch it again at a later date. If anything happens, it means that you miss an important bit that you want to rewatch, or if there's just something that particularly interests you that you want to get back on board with. There are subtitles available on this. If you can switch them on or off by clicking the CC Live transcript button at the bottom of your screen. So the series in general is to bring some of our exciting cutting-edge research from university to scientists of all ages. So whether you're at school or whether you're retired or everything in between, and you've got an interest and enthusiasm for science, we hope that we can bring you some of the interesting and exciting research being done at York. The event will take place on the second Wednesday of each month, and each time we'll have a speaker who's really at the forefront and sort of internationally recognised as somebody doing important work in a different field of physics each month. There'll be talks from all sorts of different people, from people involved in electron microscopy, so looking at the very smallest objects, to trying to explain why dark matter might be something that we can see or we can't see in the universe, to quantum communications and fusion energy, or the future of clean energy on our planet. All of these different topics link to the MOOC that we run in the physics department. It's an online course that we offer through Future Learn, which should have a link in the Q&A, so you can always have a click down there and see if you're interested in joining us for that MOOC. There will also be a link to register for that MOOC on the YouTube link once it goes live after this event. Which means I think you probably heard enough from me. I'm glad that I can now introduce our chair for the evening, who is Dr. Josie Ross. Josie's an associate lecturer in the Department of Physics, specialising in radio astronomy and high energy astrophysics. She teaches our vibrations and waves course to our first years, and also teaches the third years about galaxies as well, using our expertise of sort of practical radio astronomy to help our astrophysics labs at the Astro campus here at the university. So without further ado, I will pass on to Josie, who will chair the session and introduce our speaker for this evening. Josie, take it away.
Thanks very much, Chris. So this evening, we're joined by Phil Hasnip, who will be giving the first lecture in this webinar series. Phil is a physicist and computer programmer in the Department of Physics at the University of York. He grew up in the 1980s, where he learned about physics at school and computer programming on his dad's ZX Spectrum. Now he writes computer software to tackle problems in physics research, and is particularly interested in using quantum mechanics to discover new materials and to tackle global issues, from new medicines to climate change. He is also a Christian and is often involved in debates on issues of science and faith. When he isn't solving the Schrödinger equation, he enjoys football, jiu-jitsu, and writing stories, and he still has a soft spot for 1980s Transformers in spite of Michael Bay. Today, Phil is going to be talking to us about materials and how they can be modelled using quantum mechanics. So quantum mechanics gives us very accurate predictions, but solving the equations directly needs huge amounts of computing power. So Phil's going to explain how a clever theorem and sophisticated software can solve this issue and allow us not only to predict material properties, but even design brand new materials with properties we've never seen before. So this evening's event will take the form of a presentation from Phil, followed by questions from you, the audience. So just a reminder that you can submit questions throughout this evening's event via the Q&A button at the bottom of your screen at any time, and I'll put them to Phil at the end of his talk. Okay, so I hope you'll enjoy the lecture, and I'll now hand things over to Phil.
Thank you very much. So I thought we'd start with our discussion about how to design new materials with quantum mechanics by just a brief moment to consider what I mean when I say materials. So I don't know what you think when I say the word materials. Perhaps you think about buildings, you think about steel or timber, perhaps you think about clothing, things like cotton or wool or polyester. There are many things that might come to mind. When a scientist talks about materials, really what they're talking about is some kind of collection of atoms, which is not a gas, probably not a liquid, most probably some kind of solid. And that's about as specific as we get. So when I talk about materials, I might be talking about the kind of materials that make up the world. So minerals, for example, soils, rocks. I might be thinking about technology. I might be thinking about new device materials that could find their way into batteries or into your mobile phone or into new computers, or even into more exotic things like devices woven into your clothes so that you can power electrical devices when you walk. I might be thinking about medicines. In particular, some of the work we've done is about how molecules which have certain medicinal properties can be crystallized into tablets, packed into tablets in a way that your bodies can absorb. And in fact, I might generalize that and talk about living creatures. I might talk about our bodies. We might consider our soft tissue or our bones as materials. And we might ask questions like, why is fluoride good for your teeth, but bad for the rest of your bones, for example? Now, pretty much everything that we see in the world around us is made of atoms. Apart from the light itself, it's just about everything that we experience. And atoms, as I'm sure you know, are really quite small. How small? Well, something like 3 billionths of a meter. That would be something like maybe a carbon atom or something, a silicon atom, that kind of size. And that's a pretty small number. So to put it in context, if you were to pluck out one of your hairs, you'd probably find it was something approaching 1/10 of a millimeter across. How many atoms is that? Well, it's something like 1/3 of a million atoms. Of course, it depends on how thick your hair is a bit and exactly what atoms we're talking about. That's the kind of number we're thinking. And you might think about a 3D case, not just the width of hair. How many atoms are in a small amount of water? I've said here a milliliter. Well, it's about 33 quintillion, which is 33 million atoms in a milliliter. So it's really quite a lot. And atoms are actually made of smaller things. There's a nucleus right in the center of the atom made of protons and neutrons. And then around the nucleus are electrons. And you might have come across a sort of solar system model before where the electrons orbits the nucleus a bit like the Earth orbits the sun. But actually that turns out not to be sophisticated enough for what we'll be talking about today, because there are problems with that solar system model that can't explain the behavior of real atoms and in particular real electrons. And it's important that we do understand what real atoms do for a variety of reasons. Now, at a simple level, we want to be able to explain what we see around us. We want to be able to explain everyday phenomena. And as a scientist, I'd like to be able to explain the results of things that are a little bit less everyday, the kind of things that experimental physicists are doing around the world. But I'm a theoretical physicist, and I'd like to go beyond just shedding some light on experimental data. I'd like to be able to develop the theory and get it to a state where we can actually predict what these experiments will do beforehand. I would like to be able to say what the properties of a collection of atoms will be without needing to do measurements first. Now, there is a theory that lets us do that, and that theory is quantum mechanics. But quantum mechanics has a couple of strange things, and the key thing that I'd just like you to think about for a moment is in our certainty of measurements. So if I take what I've called here ordinary physics, the kind of physics that you learn at school, for example, if I have a particle, it could be any particle, it could be a planet or a car or a tennis ball, or in this case, an atom, and I say it's located somewhere. So I've drawn an axis here. Let's say it's located at x equals 0. There's no uncertainty in that statement normally. The particle is at x equals 0. So if I were to draw the probability of finding the particle at x equals -4, -3, -2, -1, which you see in the bottom left, it's 0 everywhere except at x equals 0. Now, that's not true in quantum mechanics. In quantum mechanics, if I say a particle is at a particular location, often what I mean is that's the average position. So on the right, I've shown you the kind of probability distribution you might get in quantum mechanics, where we see that the average position is at 0. In fact, the most likely position is at 0. I've plotted the probability, remember? But there's a probability, certain probability that it will be nearer to 1 or -1 or 2 or -2. And in fact, it only really becomes effectively 0 as I go quite a long way away from where I just told you this particle was. So in quantum mechanics, particles spread out across space. How can we predict how they spread out, and how can we predict their properties? Well, we want to solve the fundamental equation for quantum mechanics, which is the Schrödinger equation. And the key thing that I'm trying to discover is what we call the wave function. The wave function, which is often given the symbol psi, which is what I've got on here, but it's just an ordinary function, except that it depends on the positions of all of the particles in the system that I'm interested in. So if I'm interested in the behavior of, for example, a hydrogen molecule, the wave function depends on the positions of the 2 nuclei and the 2 electrons. The wave function contains all the information I need. So if I compute the wave function, I can work out any property of the system that I'd like. Okay, and there are a lot of things that I might be interested in. I might want to know whether the hydrogen molecule is bonded or not. A chemist could probably tell me that, but I might be able to predict exactly how strongly it's bonded or how reactive the molecule would be if I were to bring oxygen in, for example. Now, let's suppose I don't take my hydrogen molecule to start with. I just think about one particle. So I've got some particle. It doesn't really matter what kind of particle it is, and I'm going to compute its wave function. And to do that, I'm going to split space up into just 10 particular points along each of my usual Cartesian directions, so x, y, z. So there are 10 points in x and 10 points in y, 10 points in z, and they form a 10 by 10 by 10 grid in my 3D space. So in other words, I'm going to calculate the wave function for 1,000 points in space. How many points and how much data does that need? Well, number of points is easy. It's 1,000 points. How much data? Well, for a typical calculation, I need 16 bytes to store one number. Computers have different ways of storing numbers, but this will give me a good balance between accuracy and storage. So 1,000 numbers, 16 bytes per number, I have 16,000 bytes. So approximately 16 kilobytes. It's a very, very small amount of storage. Your phone may well have that much storage. If you have a smartwatch, it probably has that much storage. Depending on exactly what you have at home, your washing machine might have more than that storage. That's one particle. What happens when I have 2 particles? Well, when I have 2 particles, the wave function depends on both positions. And that's because the way that particle 2 spreads out is different depending on where particle 1 is. So in this case, the wave function has all the information for particle 1 and particle 2, but it also needs me to put the positions of particle 1 and particle 2 in. It depends on both positions. So now I have 1,000 possible locations for the first particle. I also have 1,000 possible locations for the second particle. So the total number of combinations I need to think about is 1,000 times 1,000, which is 1,000,000 numbers. So at 16 bytes each, that now takes 16 million bytes, which is 16 megabytes, which is still not a problem. We'll go to 3 particles. So now my wave function depends on 3 positions. And that's, again, because when I consider what particle 3 is doing, it's different depending on every possible combination of what particles 1 and 2 are doing. So now I need 1,000 times 1,000 times 1,000. So at 16 bytes per number, that gives me 16 gigabytes. And this is starting to get to the kind of storage we might care about, because my computer only has 32 gigabytes. So 16 gigabytes is half of the total system RAM that my computer has. That's for 3 particles. Well, by now you may have worked out what's happening. Whenever I add another particle, the wave function depends on 1 more position, and that position is the behavior with that position depends on all the combinations of all the particles I had before. And that means that every particle I get multiplies the size of this wave function by 1,000. So whereas 1 particle gave me 16 kilobytes, 2 particles 16 megabytes, 3 particles 16 gigabytes, if I go to 4, I'm up to terabytes. 5, I'm up to petabytes. 6, I'm up to what we call exabytes. 7, I'm up to zettabytes. 16 zettabytes is about 1/5 of the estimated total computer storage in the world this year. So if I want to study the quantum mechanics of 7 particles, I need about 1/5 of the global data storage. That's everything Google have, Microsoft has, Amazon has, all the data centers in the world. I need about 1/5 of that. And I can't do 8 electrons because that would need 1,000 times more storage. So I'm stuck at 7 particles. So that doesn't let me simulate very much of a material. How can we make the quantum mechanics easier for ourselves? How can we focus our effort where it's really needed? Well, the first thing that we might notice is that actually most of the properties of materials that we're interested in are through the chemical bonding. And the nuclei don't do the chemical bonding, that's the electrons. So is there a way we can focus our quantum mechanics just on the electrons? The second thing we might do is we might focus our effort on some of the energy states that we think are going to be the most important. And we'll talk about that a little bit later on. And the final bit is we get a computer to do it. Because what we're going to end up with is a method which is very accurate and achievable, but would be very, very slow and tedious if I had to do it with pen and paper. So we implement it in computer software and the computer runs the simulations. So let's look at this first bit. I've already said that when we look at a quantum mechanical description of a particle, that what's typically found is a particle that we think is at position 0 is actually spread out. And there's a probability of finding it at regions of space that are not exactly at 0. And I've computed the wave function for a particle that is trapped in a potential well here. If you're interested, it's actually a potential well, a bit like a spring. It's actually a parabola, an attractive potential that the electron sits in. And the wave function and the probability, I've actually plotted the probability here, not the wave function, you can see is spread out. Now, if I take exactly the same potential and I put a particle in which has more mass, so we sometimes might say that's a heavier particle, the wave function changes a little bit. It gets a little bit more peaked around 0, and it doesn't spread out quite so much. And if I keep changing the mass, the wave function gets more and more peaked at 0 and spreads less far out into the other area. So if now I was sampling just at 0 and 1 and 2 and 3 for my 10 by 10 by 10 grid, actually you see that the probability of it being at any point other than 0 is basically 0. The particle is at location 0. In other words, I've sort of gone back to my classical picture. So there's my heavy particle on the left, that's its wave function. And there's the classical picture of a particle on the right. And in fact, they're practically just about the same. If my particle has enough mass, I can use a classical approximation. Now, it turns out electrons are too light to do this. We need quantum mechanics for those. But nuclei are typically at least 2,000 times more massive than electrons. So even a single proton, like a hydrogen nucleus, is 2,000 times more massive. Carbon is something like 20,000 times more massive. And as you keep going across the periodic table, they just get more and more massive. So that means we can often treat nuclei as if they were classical particles. They also move much slower than the electrons. And so from the electrons' point of view, we can pretend that the nuclei don't move at all. They just are completely static. This is a fantastic concept. It's called the Born-Oppenheimer approximation. It lets us really focus our quantum mechanics on the electrons and treat the nuclei as slow-moving particles which are treated classically. In other words, the nuclei are very heavy, they're slow, and they're pretty boring. They don't do any chemical bonding. They just sort of sit there and influence the electrons. We don't need quantum mechanics for the nuclei. In contrast, electrons are light and they're quick. They move very rapidly and they do all the interesting things. They're the things that, for example, conduct electricity. They're the things that do the chemical bonding. They make bonds, they break bonds. And as far as they're concerned, the nuclei are a bit boring and a bit static. It's a bit like if you go down to a park, for example, there are swings and there are roundabouts. And sometimes if you go down, you'll see young children with their grandparents. And you'll see the young children running around, trying to get their grandparents to maybe walk over to the swings and give them a push. And the grandparents are plodding along, go, yes, we'll get there, we're going along. As far as the grandparents are concerned, the children are ridiculously quick. They're moving around everywhere. If they have 2 or 3 grandchildren, it's like a delocalized sea of grandchildren spread out around them. If you're the young child, the grandparents seem stationary. They're never moving. It doesn't matter. You're trying to get them to the swings and they seem to be just taking forever. In physics, we call this approximation where the nuclei are treated classically as point particles and the electrons quantum mechanically, and we sort of split off their 2 motions from each other and we consider the nuclei to be static. We call that the Born-Oppenheimer approximation. And it's great because it lets us not have to consider protons and neutrons explicitly. We can handle those separately. We can focus all our effort on the electrons. And it's so good. I've actually written a little poem as an ode to the Born-Oppenheimer approximation, which I'd like to share with you now. Electrons are light. They travel at pace with wave functions spreading all over the place. Nuclei are not. They're massive and slow. You don't need Schrödinger to see where they go. So there you are. That's my little ode to the Born-Oppenheimer approximation. Now that lets us essentially remove the nuclei from our quantum mechanics. So that means when previously I was simulating 7 particles, maybe with a fifth of the world's data storage, that would have been 1 nucleus and 6 electrons. And now it can be 7 electrons. So now I can finally model 1 atom of nitrogen. I'm not going to get a lot of chemistry out of this. I'm not really going to make a material. So what else can we do? Well, in everyday life, materials are dominated by the lowest energy state that they can be in. So if you pick up any material, wood, plastic, metal, whatever it might be, the electrons in it are pretty much all in the lowest possible state. And in fact, that there is a lowest possible state is one of the first predictions of quantum mechanics. And it's very important. It's why atoms exist at all. It's why the electrons can't just lose energy and decay into the nucleus and produce a neutral lump that doesn't react. The properties of a material depend almost entirely on this lowest energy state. And if all we're interested in is computing the lowest energy state, not all the states, we can actually use a different form of quantum mechanics. And that different form of quantum mechanics is known as density functional theory. Basically, it proves a relationship between this tricky quantum mechanical problem we had earlier and a slightly different sort of imaginary quantum mechanical case. What it says is the lowest energy state that we call the ground state, if we say it has a particular energy, I've called it E here, and the electrons are spread out with a particular probability distribution, which I've called rho of R here, there is another system which has exactly the same energy and exactly the same probability distribution. But there's a key difference. In this other system, the electrons don't directly interact with each other. So I've drawn that here as two sort of boxes. In the left here, we have our original problem with electrons all interacting with each other, and that they feel some kind of attraction to the nucleus because they're negatively charged and nuclei positively charged. So they've got some electrostatic potential, and they've got energy E and the probability distribution rho. But there's another system where the electrons don't interact with each other directly, and they move in the potential that the nuclei feel, and also a slightly modified potential. We have to add an extra potential, but as long as we add the correct extra potential, that system also has the ground state energy E, lowest energy state E, and the probability distribution given by the same function rho. And density functional theory shows us that these two systems are identical, and it tells us that this extra potential we've added to make them the same exists, that it's there to be found. Why is that such a good idea? Well, it was a good idea. It was pretty much a revolution that started with the first paper, which showed the link I've just said. That was in 1964. The reason it's a revolution wasn't immediately clear to scientists, but it's become clear over the intervening time. By focusing our effort on the probability distribution, rho of R, not the wave function itself, we save a huge amount of computer storage and computer time. So the probability density, this rho of R, tells you how many electrons you expect to find at any point in space. And it tells you it for any point in space that you care to pick. And the important thing is, it's a point in space. I don't care where particle 1 is, particle 2 is, particle 3 is, particle 4 is. All I'm saying is, at this point here in space, what is the probability of finding an electron? In fact, what are the expected number of electrons that I might find there? Because it only depends in 3D space, if I've split space into a 10 by 10 by 10 grid, like I did in my earlier example, it has 1,000 data points. Not 1,000 data points per particle, just 1,000 data points. And that means that the storage scales very, very nicely with particles. So here's the same table I showed you earlier with the storage for ordinary quantum mechanics, and now with density functional theory. So if I only have one particle, there are no other particles to interact. So they both take 16 kilobytes. They both need my 10 by 10 by 10 grid. But with two particles, ordinary quantum mechanics took 16 megabytes. Density functional theory still only cares about the 1,000 points in space. The probability distribution, the values have changed. So now you might expect there are regions where the probability of finding an electron is higher because there are 2 electrons in there. There might even be regions where the expected number of electrons is now more than 1 because there are 2 electrons that could be there. But I only need to define it on my 10 by 10 by 10 grid. I can increase the number of particles. The FT doesn't care. 4 particles, 5 particles, 6 particles, 7 particles, a fifth of the world's data storage. Oh no, says density functional theory, that'll fit on your smartwatch, no problem at all. So this is why it was such a revolution. And this is why people became very interested in practical simulations, getting quantum mechanics that we can really apply to real materials problems. What kind of things can we do then? Well, I've drawn here, this is an organic chemistry textbook example. So if you do organic chemistry, you might recognize this notation, but don't worry if you don't, I'll just talk you through it. This is a hexagon made of carbon. So there are 6 carbon atoms in a hexagon. One of the carbon atoms is bound to oxygen, that's the big O, and the oxygen has got a sodium atom, that's the Na next to it. And if you're a chemist, you might realize that probably what will happen is that sodium will lose an electron to oxygen. And that's in fact what you'll find in most chemistry textbooks. And they're bound together by that attraction between the resulting negative and positive charge. Now, I told you one of the carbons was bound to oxygen. What about the other 5? Well, they have hydrogen on there. Hydrogen is so commonplace in organic chemistry that people don't bother to put it on. You just have to know that it's there. But there are hydrogens kind of coming out of this hexagon like spokes on a wheel. Now, why am I showing you this? Well, I'm showing you this because I'm going to show you the result of doing a density functional theory calculation. And I'm going to run the calculation like this. I'm going to throw a bunch of electrons into a sheet with this, the nuclei for these atoms in this structure in the middle of the sheet. And then I'm going to tell a computer, lower the energy. So I'm going to throw the electrons in randomly. Let's see if we can get a random throwing in. There's my random throwing in. So dark areas means not many electrons. Light areas mean lots of electrons, okay? And I throw them in randomly, which means I start with this kind of mush of electrons. What happens as I get the computer to refine it, and it will refine it in a series of about 10 steps. So you'll see jumps as it refines it. Now, what you'll see here is that electrons very, very quickly go from being randomly smeared in space to sitting on something that looks very much like a molecule. But what I particularly like to point out is you can see the hexagon, you can see these lobes of electrons going out to the hydrogens, you can see bright blobs of charge with the oxygen and the sodium, which both have a lot of electrons. And all of the chemistry, all of the bonding that, for example, at school you're taught and you just learned that that's what will happen, has emerged just from the quantum mechanics. At no point did I put in that the bonding is, for example, covalent bonding or metallic bonding or ionic bonding. I didn't bother with that. I said, these are where the nuclei are. What will the electrons do? That's all I asked. So we really do have all of the ingredients we need now to make predictions. So what shall we apply our newfound capabilities to? Well, here is something that I suggest is a global challenge. This is the global energy consumption in petawatt hours per year. Okay, not kilowatt hours like you might use at home, petawatt hours. This is from a statistical review that BP did a few years ago. And I think you can see there is a fairly clear trend here that we are using more and more and more energy every year. And this isn't sustainable. It's actually not sustainable, even if you discount climate change, although obviously climate change is a big cause for concern. What can we do? Well, there are lots of things we can do. We could change our habits, of course, and we can look for doing things a different way. But one thing that we've been looking at is, where is this energy used? And in particular, is this energy always used wisely? And the answer is no. In fact, there's a lot of points in our generation, transmission, and consumption of energy, say electrical energy, where electrical energy is lost as heat. So wires warm up, for example. Devices warm up. You might know if you're playing a game on your mobile phone, the mobile phone can get quite warm. If you're playing a game on a laptop, you might hear the fan kick in. It might even be heating the things on your desk. That heat is just vented into the atmosphere. It's lost. But is there something we can do that's better than that? Well, there is. And we can exploit what's called the Seebeck effect. So here's a diagram. This is from Wikipedia, from their thermoelectric generator page. The basic idea is this. I'm just going to give you an outline for what happens. I make a device which has actually two materials in it. There's a hot side and there's a cold side. Now, I'm going to give you a simple explanation. The realistic explanation is slightly more subtle, but this will give you the basic idea. At the hot side, all of the charge-carrying particles, which is electrons in one material, negatively charged, you can see that on the left in the blue, they heat up. And when they heat up, they start to move. And they move in all sorts of directions. In the cold side, they don't move so much. And so that means that over time, the electrons will move from the hot side towards the cold side. They'll carry charge. And if all I do is do that, then eventually the negative charge that builds up on the cold side will apply a force to the rest of the electrons, and it will stop electrons moving from the hot side to the cold side. So if I just do this with one of these materials, what I see is I get a negative buildup of negative charge on the cold side and a slight positive charge on the hot side. But now I do something a little bit different. Now I take a material and I remove some electrons so that there's some net positive charges. And that's what I've done with the yellow material on the right-hand side. Now what happens is, at the hot end, those positive charges move around. These are a bit like bubbles. So they're not real positive particles, they're gaps in the electrons. But just like bubbles, they behave as if they were particles with the opposite properties to the fluid around them, which in this case are the negatively charged electrons, so the bubbles appear positively charged. At the hot end, these positive charges heat up and they move around a lot and they slowly move through the material. So in the yellow material, what I end up with is a buildup of positive charge at the cold side and negative charge at the hot side. And if that was the only material, that's where it would end. But now you put them together like we have in this diagram, and now you can see that what we could do is we could electrically join the two materials together, and now anywhere that a negative charge built up in one and a positive charge built up on the other, the negative charges can move towards the positive charges to neutralize them, and that is an electrical current. And that's the basic idea behind a thermoelectric generator, that we convert this change in heat into an electrical current, actually an electrical potential, which drives a current. So we want to use this to convert waste heat into electricity. We want the hot side to be maybe a car exhaust system or an industrial power plant, maybe a cooling tower at a power generator. When we look at the Seebeck effect, there's a thing we call the figure of merit, ZT. It's just a number that tells us how good a material is at converting heat into electricity. It's got a formal definition, which I've put here in case you're interested, but I just want to pick out the components and give you the basic idea. The first thing is there's a coefficient S, which is a number that is just different from material to material. We're going to consider that to be a constant today. So that's just a constant depending on the material that you pick. Then there's this symbol sigma, which is a conventional symbol for the electrical conductivity. Then there's the temperature. And then we divide all that by kappa, the thermal conductivity. So if I want it to be a really good thermoelectric, what this is telling me is I want a really high electrical conductivity so I can carry the charge carriers through the material really, really efficiently. But I want a very low thermal conductivity so that I keep one hot side and one cold side. I don't want all the heat to go from the hot side to the cold side and end up with a sort of lukewarm material, because then there's no temperature gradient. There's nothing to create more electricity. So I want to keep the temperature gradient, but I want to keep generating charge. And this is a tricky thing to do because it's quite common in many materials that the things that carry electricity also carry heat. But we can do that if we take semiconductors. So we can take a semiconductor. It could be a common one like silicon, although silicon's not normally very good for this because its Seebeck coefficient is quite poor and the thermal conductivity is really high. But we take a semiconductor, we add some extra atoms with extra electrons or fewer electrons, and that's called doping. And that gives extra carriers of electrical charge. So that improves its electrical conductivity massively. And we want to stop heat going through the material. So ideally, we want to introduce maybe some kind of defects into the material so that as the heat moves through it, it will bounce off these defects and scatter, and that will really slow the rate at which heat goes through the material, and it will lower kappa. And that will give me a nice big ZT, which is to say it gives me a really efficient thermoelectric. Now I'm just going to focus on one particular material that we've looked at in the last couple of years. Just to give you a general idea, if you just go to Amazon and buy a thermoelectric chip, and you can buy them, their ZT is poor. It's typically something like 0.1 or 0.2, and a really good commercial material might have up to maybe a half. But we want a ZT much bigger than that. Really, we'd like it to be over 1, ideally over 2, even over 3. The higher, the better. But 0.1, 0.2, even 0.5 just doesn't cut it when we're looking at these global issues. Now, recently, in the last perhaps 3 years, a compound called niobium iron antimonide has gained a lot of interest. It has a high power factor, which is what we call the S squared sigma bit in the ZT calculation. And in fact, has a high ZT. So it's a pretty good thermoelectric, and it can generate a lot of power. That's what the power factor controls. Now, we applied density functional theory to this material, and we computed how good a thermoelectric it was. It was known to be good experimentally, but does DFT agree? And actually, how good it is depends on the temperature. So I've done a plot here of the temperature, that's the horizontal axis, and on the vertical axis, I've plotted how many extra charge carriers I've put in. So how I've doped the material. And then in the colors, you can see what ZT it has, everywhere from basically nothing through to the sort of the medium blues, which is what's readily available commercially, to the sort of light greens, which is the good commercial materials. And you can see here that at high temperatures, about 1,000 Kelvin, and the higher doping concentrations, we're getting a ZT of about 1. So we're getting this material should be about twice as good as standard good thermoelectric materials. So this is very, very promising, but we didn't stop there because we thought to ourselves, well, is there a way to make it better? Maybe we could introduce some more impurities and we could see about scattering even more heat. So what we did is we took the niobium in this material and we swapped it for tantalum. Now, the reason we swapped it for tantalum is it's in the same column of the periodic table, so the chemistry should be similar. We expect the material to be basically still pretty good. But tantalum is heavier, and it's heavier than the iron, for example. And whenever you have a difference in how heavy atoms are, there is the possibility that that difference will cause vibrations which are carrying heat and moving through the material to be scattered more. So in other words, by choosing a heavier element, it disrupts the heat traveling through the material that will reduce the thermal conductivity and will drive up our figure of merit. Does this material even exist, though? We've literally just in my computer taken out niobium and put in tantalum. Well, the good news is we did that, and the density functional theory calculations predict that the material exists. It predicts the material structure, which is the same as niobium iron antimonide, as we hoped. And it predicts that the ZT is increased. The thermal conductivity goes down and ZT is increased. How much is it increased? We'll see for yourselves. This is exactly the same plot that I showed before, but now for tantalum iron antimonide. And you can see that at 1000 Kelvin and at the similar doping concentrations to before, we're getting a ZT which has gone from around 1 up to 1.5. This is 50% better than one of the previous top research level thermoelectric materials. And I'm delighted to say that very recently this has been synthesized experimentally, and the early results show that it is indeed an extremely good thermoelectric. Well, that's pretty much all we have time to go into today. So just in summary, I hope I've shown you that with quantum mechanics, we genuinely can predict the behavior of electrons. In particular, using density functional theory, we can make very practical calculations for real materials, in fact, real chemicals, very similar ideas in gases and fluids. And we can put these together to predict the behavior of real materials in real situations for genuine technological applications. We can predict a huge number of properties for all kinds of materials and chemicals, and we can start asking questions. If we know how to compute the energy, we can ask questions like, well, how would the energy change if I change the chemical environment? And that might tell me how reactive a material is. I might ask, how does the energy change if I squeeze the material? That might tell us how strong the material is. We can ask, how does the energy change as I move the atoms back and forth as if they're vibrating? That gives me the vibrational frequencies. I can predict all sorts of properties from the color, how they interact with light, how tough they are, of course, how heavy they are, and as you've seen, how stable they are and what their thermoelectric properties are. I could go on for probably a whole other webinar, but I won't. I'll stop there. So I hope you found that interesting. Thank you very much for listening, and I'll open it up for any questions.
Thanks very much, Phil. That was a fascinating talk. I really enjoyed your example of grandparents in a playground to explain the Born-Oppenheimer approximation, and of course your poem. So we have some questions from the audience then. I'll start with those that are directly related to what you were talking about today. So firstly, in terms of the DFT then, are we saying that a point in space can have more than one particle occupying it?
That's a good question. So in quantum mechanics, particles, we often think of particles as not being able to occupy the same point in space. But what we actually mean is they can't have exactly the same state. So what that means is there is a probability of finding more than one electron instantaneously. For example, the probability can go in one region of space above 1. So we talk about the expected number of electrons. We're talking about how many electrons there are per element of volume, though. We're never actually saying literally a point in space, because that would pretty much have zero volume. It has what we call infinitesimal volume. So the chance of finding anything in an infinitesimal volume is effectively zero. What we're after is how many electrons do we expect to find in some small but not zero volume of space? And yes, that can go above 1, 2, 3, 4, 5. I've done simulations in neutron stars where this number gets really quite big. So I told you we consider materials to be quite general. So neutron stars are materials.
Great, thank you. And in terms of that coloured image of the benzene ring with oxygen and sodium, how are you able to get it to show the lower energy structure and lobes of electrons?
So what I've plotted there is the probability distribution of all of the electrons, actually all the bonding electrons in this molecule. So the reason the dark, maybe I'll, can I just skip back to that one? So if we just let that run. So this is straight from the computer simulation. It's a 3D simulation, but I've taken a slice through the plane of the molecule. It's quite helpful that the molecule is flat for this. And these bright blobs for oxygen and sodium, so they're bright on oxygen because it's gained the electron from the sodium, and it's bright on sodium because actually sodium has quite a lot of electrons. It's on quite a low down row on the periodic table, lower than oxygen. So when I do this, in one sense, this comes directly from solving the Schrödinger equation and asking, where are the electrons likely to go? And the answer, in accordance with chemical intuition, is they want to go on the molecule, but they mostly want to go in between the atoms where they're sharing a covalent bond, or on the oxygen, and there are a few very low energy electrons sitting on the sodium. This doesn't tell you things you might know from chemistry about whether they're in 1s or 2s orbitals or 2p orbitals. You have to work a bit harder to get that information, but it tells you what's actually physically observable. This could actually be seen in an electron microscope, for example.
Okay, thank you. So for these ZT materials, is it trial and error to find a high ZT material, or is there a way to use theory to predict if a material will have a high ZT value? That's
a great question. Yes. So let me just skip to the ingredients. So there are three basic ingredients. The temperature is usually controlled by the application. We don't normally get to choose how hot our power station runs, for example. So T is given to us as part of the problem. The material has a particular Seebeck coefficient. That's S in this equation. There are actually a couple of things you can do about it, but roughly speaking, that's a given for a material. So our job as theorists, when we're trying to design a new material, is to tailor sigma and kappa. Now, sigma we can control by doping. That is a theoretical prediction, but it's so well known and so well understood since the sort of 1950s, 1960s that we don't really think about that as a prediction of quantum mechanics. It's just everybody's taught it now when they go to university, but it's fairly easy to do. The trick is to disrupt the heat without disrupting the electrical current. So you can put loads of defects in your material and that will disrupt the way heat goes through, thermal conductivity will drop, but it will also make your material very electrically resistive as well, which is bad. So the trick is how you can engineer things so that electrically there's not many defects, but thermally there are lots of defects. And often that involves trying not to change the chemistry too much. So that's why I swapped tantalum in for niobium and not one of the other elements, because tantalum is in the same column of the periodic table. I expected that not to disrupt the chemistry. I haven't assumed that. I've predicted its behavior using the quantum mechanical solution, but the reason I chose tantalum was to do that. Now, as for trial and error, the great thing is in a computer, you can automate it. So in a computer, you can very, very rapidly swap tantalum for anything you like. You can make a mixture of niobium tantalum, which is in fact what we're looking at the moment. You can change anything you like about the material. You don't have to worry about how hard is it to get that material, how costly is it to refine it. Do we have any at the university at the moment? Do I have to buy some in? I don't have to worry about that. I change one number, which is basically how many protons are in the nucleus. That's all the simulation cares about. It's a number. Change that number, add or take away electrons to make it neutral. I'm done. And of course, I can then get clever, design things you might have heard of, like genetic algorithms that go on top of this and do something a little bit better than trial and error, and slowly learn what makes a good thermoelectric. But that's, again, a different webinar.
Okay, the final question that we'll finish with, on what kind of scale is this thermoelectrics method applicable?
Okay, there's several ways I could interpret that. If you mean industrial scale, then the great thing about a thermoelectric is there are no moving parts. So it can go really, really small, which means you can get them very, very close to whatever is designing this. So for example, we've got some exploratory talks with Intel about putting this actually on a CPU. In fact, maybe even within a CPU, but they can't do that yet, but actually on a CPU. On the other hand, if these are earth-abundant materials, there's no particular reason why you can't mass produce them. So you can't produce really, really large amounts of this. It just depends how hard it is to make things, and how much, and of course, how much there is in the Earth's crust.
Okay, brilliant. I think that's all we have time for today. I'd like to thank Phil again for his time and for talking to us all today. The recording of this event will be made available on the Department of Physics YouTube channel, and the link to this will be sent to all ticket holders. A reminder that if you'd like to find out more about this and other research taking place here in the Physics Department, a link to our online course with FutureLearn is being shared in the chat. So thank you all for joining us this evening, and I hope you enjoy the rest of your evening.